Hello and welcome to my presentation. Today I present our research on the topic of economic scheduling of multi-microgrid systems considering power grid expansion costs. We are from the Institute of Factory Automation and Production System at the Friedrich-Alexander-Universität Erlangen-Nuremberg in Germany. The structure of the presentation is as follows. First I introduce the topic and its background, then I will go into the methodology used here. In the next sections, I present the model of the multi-microgrid system and the economic analysis. After presenting the results in section 5, I discuss the conclusions. Many energy systems around the world are currently undergoing a transformation from centralized to decentralized energy systems. Therefore, so-called multi-microgrids are created from existing distribution grids. In these systems, the focus is not only on the economic operation of individual microgrids, but also on the power flows between the microgrids and the superordinate grid. Therefore, for cost-efficient implementation of multi-microgrids, not only the economic operation, but also cost-efficient design, which means investment costs and grid, of the multi-microgrid must be ensured. In most cases, the two types of costs are opposite. The more electricity exchanged between microgrids and main grid, the lower the operation costs and the higher the associated investment costs in the grid, and vice versa. Therefore, economic planning to achieve optimal cost structure of multi-microgrids is an important research focus for a cost-efficient future distribution grid. We are therefore researching the cost-efficient planning of multi-microgrid energy systems. There are two different levels of interest to consider here. On the level of multi-microgrids, there is interest to invest as little as possible in the grid expansion, but to buy as much cheap electricity as possible. On the other hand, the individual microgrids want to optimize themselves by having a high self-consumption and therefore interacting as little as possible with the higher level system. Therefore, I would like to address three aspects in this presentation. A methodological approach for economically efficient grid expansion planning of multi-microgrids, considering the investment cost of multi-microgrids and the power operating cost of the connected microgrids. The validation of this approach by presenting results of the model-based analysis. And finally, the identification of the most important factors influencing the economic dimensioning of multi-microgrid expansion based on different case studies. Methodology aims to determine the most cost-efficient grid expansion under given initial conditions, considering the operating costs and the investment costs for the multi-microgrid. This requires two models, one for microgrid scheduling and one for testing the feasibility of the power grid. We proceeded as follows. First, we created an initial state for the microgrids here called case study, as well as a linked optimization model for scheduling. After planning and defining a multi-microgrid model, we analyzed whether power system parameters were violated or not. If not, the use of the multi-microgrid had to be constrained for the microgrids. We did this with the grid connection power, which was reduced until scheduling led to a valid grid state. If this grid state is valid in every period, the operational investment cost can be added. If the simulation was performed with several grids, the cost can be used to see which grid is the economically efficient one. The different grids are defined as the same grid topology with lines of different strength. For the multi-microgrid, a medium voltage grid is used with interconnected microgrids in an open mid-voltage ring test grid. Here, the microgrids try to minimize the operating costs and use a common mid-voltage grid for this purpose. If investments want to be made in the multi-microgrid, these investment costs are distributed equally among the connected microgrids. The grid connection power of all microgrids to a mid-voltage grid is also equally distributed. For the microgrids, this means that an investment is economically efficient if they achieve a greater reduction in operating cost over the depreciation period when the initial must invest in a mid-voltage grid. A microgrid was selected with 1,150 households, with prosumers and consumers only, which submit their demand and control of their assets to a central planner and follows its schedule. Here, a prosumer has electricity generators or flexible electricity consumption technologies. The consumer-only household has only a discrete static electricity load. For the analysis, we varied both power generators and consumer technologies in terms of technical specification and market penetration and examined in different case studies. For the grid expansion, we assumed a starting grid because all prosumers were once normal pure consumers. For this condition, an initial grid was developed, which can be reinforced to different degrees in different scenarios. The scenarios of grid expansion are parallel installed power lines. The scenarios are called grid 1 for an unreinforced grid, grid 2 for a grid reinforced with one parallel line, and grid 3 for a grid reinforced with two parallel lines. Since investment and operating costs are allocated to different periods, both types of cost had to be calculated for the same period using the net present value method. The influencing factor included the depreciation period of the investment and the interest rate. Some parameters were varied to draw conclusion, such as electricity prices to show the influence of volatility, prosumer penetration, electricity generators, and the flexibility of electric vehicles and heat pumps. The results show, depending on the initial conditions, different degrees of grid expansion are economically efficient. In the first microgrid case study with 27 simulations, PV with battery storage is implemented at prosumers, and power for electric vehicles and heat pumps are maximal. The results of the scenarios are shown in Table 1. Here it can be seen that only with low penetration of prosumers, grid 1 and grid 2 are the most economically efficient solutions. For higher penetration, grid 3 is the most economically efficient. In the next case study with 27 simulations, instead of PV and battery storage in prosumer households, a large central wind plant is implemented in the microgrids, and the power for electric vehicles and heat pumps are still at maximum. The results of these scenarios are shown in Table 2. Here, for low penetrations, economic superiority of the non-expanded grid results. At 40% penetration, the influence of electricity price volatility is evident. The more volatile, the more likely it is worthwhile to expand the grid. Thus, at low volatilities with electricity prices, the non-expanded grid is still economically more efficient, and at high volatilities, grid 3. For high prosumer penetrations, only grid 3, the most expanded grid, is economically most efficient. In the last case study, a wind plant is implemented in the microgrid instead of PV and battery storage again, and now the power for electricity vehicles and heat pumps is now at minimum. The results of these scenarios are shown in Table 3. Based on these results, no influences of the volatility of the electricity prices can be identified. Since only the power of electric vehicles and heat pumps was changed here, it shows that the more inflexible the assets of the prosumers, the less worthwhile a grid expansion is. It can be concluded that for an economically efficient multi-microgrid, the investment cost of grid expansion must be considered in the microgrid scheduling. The results show that the trade-off between operational cost and investment cost depends on the design of the microgrid and the structure of the wholesale electricity prices. The more flexible the microgrids are, the more beneficial it is to expand the multi-microgrid. When it comes to wholesale prices, the more volatile prices are, the more advantageous it is to expand the multi-microgrid. Thank you for your attention. I hope you enjoyed this presentation.